Okay, everybody, this is Miss Pi again. In this video, we're going to go over some rational functions and how to find the vertical asymptotes, removable discontinuity, and then the x-intercepts of your rational functions. Okay, couple things to note. Anytime you see an equation like this where you have some formula in the numerator and some formula in the denominator, in the textbooks and on the worksheets and everything, you're going to see n of x, and that just means the equation in the numerator. And then sometimes you'll see d of x, and that just means the equation in the denominator, okay? So don't start freaking out thinking these are new, weird, crazy equations. They're just whatever's in the denominator and whatever's in the numerator. Okay, so let's go ahead and get started on filling out these notes about rational functions and discontinuity. Okay, so rational functions in the form of f of x equals something, an equation in the numerator divided by an equation in the denominator, are undefined as values of x that make the denominator equal to 0. So you just take your denominator, set it equal to 0, and solve for x. Okay, same thing, same principle that we were doing with our polynomials when we solved for x and tried to get our solutions, or our x-intercepts or zeros. Okay, we're going to do the same thing with rational functions, except we're going to break it down into the equation in the denominator and the equation in the numerator. Okay, so anytime your denominator, if you plug in some number in for x in the denominator and you get 0, you're going to cause a break or an undefined term to happen, or it's undefined at that whatever number you plugged in for x. Okay, so this is called discontinuity, and it can take a couple different forms. If you have an asymptote, in this case a vertical asymptote, remember those are the vertical dotted lines where your graph can't cross, or it could be removable discontinuity. In just a minute I'll show you what both of those look like. I know most of you are very familiar with vertical asymptotes, and it doesn't matter what the equation is. If you set your denominator equal to 0 and you solve for x, and whatever number you get or numbers you get for that, those will be your zeros of the denominator. Okay, so if you have a 0 in the denominator but it is not also a 0 of the numerator, then you're going to have a vertical asymptote at that 0. If you set your numerator equal to 0 and you get the same solution as you do when you set your denominator equal to 0 and solve for x, so it's said to be a 0 of both the numerator and the denominator, then you're going to have what's called removable discontinuity. Okay. These instructions here, I forgot to cut them off of your notes. They were part of last year's worksheets, but it does kind of explain how you're going to find your zeros in the denominator and the numerator, and how to find the location of your vertical asymptote and removable discontinuity. Okay, so let's just briefly go through them. Actually, let me see if I have them over here. Yep, I do. All right, so for the rational functions given, factor if possible to identify more easily the zeros in the numerator and the denominator. We discussed that in our unit on polynomials. Anytime you have your equation factored, it's much easier to find your solutions. Okay, and then list the values of x at which the function is undefined and use these to describe the function's domain. Okay, finally decide which of these values provides the location of a vertical asymptote and which denotes removable discontinuity. Okay, so we already went through the difference, or the different rules. If it's a 0 of the denominator but not the numerator, you have a vertical asymptote. If it's a 0 of both, you're going to have removable discontinuity. All right, so let's look at this. This is an example of two different formulas. So I've graphed the equation x minus 4 divided by x plus 2. I also graphed the equation x minus 4 divided by x squared minus 2x minus 8. Okay, so this equation is already set up in factor form, And if we look for the zeros of our denominator here, we would set x plus 2, set that equal to 0, and solve for x, and you get x equals -2. Okay? Now, if you set the numerator equal to 0 and solve for x, you get x equals +4. Okay? So notice these solutions, or these zeros, are not the same values here. Okay? So now let's leave this for now and let's look at this equation here. You want to set both, the numerator's already factored. You want to factor the denominator. Okay, let me see if this is, yep, that's the one I want to get rid of. So when you factor the denominator, this is what you get. And notice how you have the factor x minus 4 and x minus 4 in the numerator and the denominator, and then you just have x plus 2 in the denominator here. Okay, so from the numerator, you set that equal to 0, and your solution, or your 0, whichever one you want to call it, is going to be x equals 4. Okay, when you set this equal to 0 and solve for x, you get x equals 4, and then over here you get x equals -2, right? There we go. So you'll see that both of these terms have both the equation over here and the equation over here, you have x equals -2 as one of the zeros. Okay, because you have it in both locations, you're going to have a vertical asymptote for both of those functions at x equals -2. Okay, there's my vertical asymptote for both of them. Now, the blue graph has the numerators has x equals 4 for a 0. And because you don't also have an x equals 4 in the denominator, that's going to be, excuse me, that is going to be a x-intercept, okay? So anytime you have the zeros from the numerator that are not also zeros from the denominator will become x-intercepts. So if you see this graph down here, when x is 4, your y is 0, you get an x-intercept right there, okay? On the other hand, on the red graph, where you have x equals 4 here, you also have x equals 4 here. Instead of a x-intercept, you have this removable discontinuity. And honestly, when you graph this, you won't see this little tiny hole right here. But if you look up the table, it'll just say undefined, okay? So like if you pulled up the table, you'd have x and you'd have f of x. Let me put that in parentheses, make sure it's the right format. Okay, there we go. We have x and we have f of x. When x was 4, it would be undefined. UND for undefined. Okay, and that just means, excuse me, because notice how right here by the asymptotes, the graph has this really sharp increase here and really sharp decrease here. But right here, it just keeps on going on. And if you graph this, you will not see this little hole right there. Okay, in fact, let me just move it. No, I don't want to do that. Let me just move it. What the heck did I do? You know what? Let's get rid of it. This picture right here is just a copy of the graph that I plugged into the calculator. Notice the graph does not show it to you here, but it is definitely, when you pull up your table and you look at 4 for x, it'll say undefined for your y value, okay? And basically, if you are going to hand draw the graph to show or to indicate your removable discontinuity, you would draw a little circle and you would leave it open like that to indicate that it is not filled in. All right, so that covers how to find your vertical asymptotes and removable discontinuity and your x-intercepts. Okay. Next video, we'll go over your horizontal asymptotes. All right. Bye.